สวัสดีค่ะ Okay, so next class will be with Ajahn Jindarat, okay? Next Thursday, and the class start at 8:30. Yes, not here, but in the CHE building. Can you remember where? Okay, what is the room? 301, okay, 301, okay, on the third floor. Maybe it must be the same room. But you have to check with the Ajahn Jindarat again, okay? Because she's not sure about the place also. So next week we have one more class on Monday afternoon. Okay? So on Monday afternoon, it will be the last time. I want to start at 1:30. บ่ายโมงครึ่งวันจันทร์ได้ไหมอาจารย์นัดแล้วนะวันจันทร์หน้าใช่ปะทำไมสองคนทำหน้างงเอาจริงนะเพราะว่าอาทิตย์หน้าสำคัญมากนะบอกได้เลยว่าคลาสสุดท้ายจะสำคัญที่สุดนะถ้าไม่มาก็อดนะอาจารย์จะบอกว่าอาจารย์ออกอะไรบ้างนั่นไม่หรอกแต่จะบอกว่าออกหัวข้ออะไรบ้างนะอาจารย์จะสรุปให้ด้วยอาทิตย์หน้าบอกเพื่อนๆให้มากันด้วย so about the place this room is not free on Monday afternoon but they propose another room on the second floor but I don't know where is do you know where is the room on the second floor okay I have to check okay I will check with them during break I tell you okay so the last time we started about vinyl halogen compounds and the synthesis and the corresponding synthesis okay so the most important vinyl halogen is VCM vinyl chloride monomer this one VCM so VCM could be produced first from ethylene and ethylene is converted to 1,2-dichloroethane with EDC abbreviation. So in this chapter you will see a lot of abbreviation, but it's not very difficult. Okay, EDC could be transformed to VCM with double bond. Okay, and the end product of VCM corresponds to PVC. This is the polymer of VCM. I think everybody knows the polyvinyl chloride product, okay? So PVC is used for the production of plastic tube, the blue one, the blue plastic tube, and also a lot of plastic sheets were made with PVC resin, okay? So in this chapter we focus on the two halogen. The first one is chloride. And the second one is fluoride. If you can remember the chemistry of fluoride and chloride, you can remember that they are different in reactivity and also the synthesis. Okay, so this chapter is very similar to the chapter concerning chloromethane and CFC from the first chapter, if you can remember. Okay, so the reaction that we use to introduce chloride atom to carbon and introduction of fluoride atom to carbon are different because chloride and fluoride don't have the same reactivity. Okay, so first we consider the case of vinyl chloride. Okay, so what is the structure of vinyl chloride? Vinyl is double bond. Okay, and chloride is one chloride atom is connected to this double bond. So you have how many hydrogen on VCM compound? How many hydrogen atoms? Just count. 1, 2, 3. Okay, so you have 3 hydrogen and 1 chloride connect to double bond. This is VCM. So, how to produce double bond? You have 2 different methods. Okay, double bond could be produced from addition and elimination. So this one is elimination. So in chemistry, you can produce double bond Why these two reactions, elimination, not elimination, elimination. The starting material of addition and elimination reaction just different. If you start from the triple bonds, here is triple bond, okay? This is a triple bond. You want to convert onto double bond, so you have to add another compound to triple bonds, okay? And you can obtain double bonds. This one is the partial addition of hydrogen chloride to acetylene, for example. But this synthetic method is not very applied in industry, okay? So the most important pathway, okay, synthetic pathway in industry is the second one. You have to start from ethylene. So how to choose the synthetic route in industry is easy. We choose the low cost starting material and the easiest method. Okay, because the cost of the production depends on how difficulty of the method is and also the price of the starting material. Okay, so in this case, you can choose the second method because ethylene is has lower price than acetylene. That's why. And acetylene is more difficult to handle because it risks to explode sometimes. So ethylene is low cost because you can produce ethylene from which method? This is a question. Can you remember how to produce ethylene in industry? Some comment. What is the raw material of ethylene? You have different raw material, but the most important raw material of ethylene. Really forget how to produce olefin, lower olefin. Okay, I know it was before midterm, but you forget everything from cracking. So if you crack from the hydrocarbon, so you can start from oil. You crack hydrocarbon to olefins like ethylene or propylene. Okay, so it's not expensive, right? So you can start from ethylene. What is the nature of the first reaction? This one is the first step, okay? This one is also the first step. You have ethylene chlorination or oxychlorination of ethylene. The first one and this one are the same step. You have two choices. You can chlorinate ethylene by using chlorine gas and heat. Okay, but you can choose the alternative method of chlorination also, which is oxychlorination. I introduced you first time oxychlorination. I remember in the first chapter when I talk about chloromethane. When you want to chlorinate methane, you have the alternative method, which is oxychlorination of methane also. This is the same. So the reactant just different from the normal chlorination and the oxychlorination method. Okay, so you can choose chlorination or oxychlorination. You can choose one. So chlorination requires chlorine gas and heat, but oxychlorination requires different starting material. So you need hydrochloric acid in presence of oxygen gas. Anyway, you obtain the same product, which is EDC. Okay, so EDC is 1,2-dichloroethane. In the structure of EDC, you don't have any double bonds, right? You have only single bond because the addition reactions, the chlorination is addition reaction. This chlorination. So this chlorination does convert bond to single bond by the addition of chloride. Okay, you have single here and two atoms of chloride and one atom It's very elimination must be out because double bond. If you can put double bond eliminated form bonds. So this what do you eliminate? What eliminate? This one. So you by hydrochloric acid eliminate the ED. So you can produce double bond. This is the vinyl, okay? One chloride remain in the vinyl. You want to see this one chloride. You have to introduce two chloride. Starting by any chloride possible, and you eliminate one chloride with hydrogen atom at the end of the process to obtain double bonds. So the last step must be the elimination of hydrochloric acid. It's always like this. So dehydrogenation to grow. So you introduce and last step test you can value so also another alternative method. The last one just combine step together, okay? Because in this case, this one, the second case, you have different steps, two steps, coordination and elimination. But for alternative method, direct method from ethane, you can start from ethane. Okay, all step together. So you mix chlorine gas. Every step does occur at the same time. So what happened in the reactor? So ethane is converted to ethylene of chlorine gas. So how is possible? This is possible because in presence of chlorine, ethane is chlorinated. So, but this chlorination, this chlorination, this is also chlorination. The name is chlorination, but this is the same chlorination as the production of EDC. This one is also chlorination. This one is also chlorination. So you can produce, you see, one chloride, you substitute hydrogen of ethane by one chloride, now you have this one. This is chlorination, but the nature of the reaction are the same or different. This one is addition, okay? But from ethane to chloride with chlorine, this one is radical substitution, okay? So you just substitute hydrogen by chloride atom, chloride radical. And in this condition, hydrogen chloride could be eliminated. So you produce ethylene. And okay, after ethylene, you repeat the same. You chlorinate ethylene by addition into double bonds. Okay? And the last step must be elimination reactions. So you just play between addition or radical substitution and also elimination. You must be able to distinguish between the different reactions. So the name is the same, coordination, but they don't have the same nature. Okay. So I can conclude in this slide. I didn't show you last time. But okay, I can repeat again. Okay. Autofocus. So how many methods for the coordination เอ๊ะทำไมมันไม่ชัดมีปัญหาทุกทีเลยอะไรของเขาเนี่ยโอ้ยจะให้เข้าใจทำไมมันไม่เคยชัดเลยโอเคso how to introduce chloride atom okay to the molecules in this chapter only okay we focus on two different reactions so the first one is addition if you start from double bond I just repeat the same reaction how many times I don't know 100 times huh? This is addition reaction. You can call this one coordination also. And the second one, if you start from single bond, you can also coordinate by using chloride radical. Okay, that's all. What is the byproduct here? HCl. So the nature of the reaction are different. Okay, the first one is addition, and the second one is radical reaction or radical substitution. So this one is radical. Okay, in the second part, I will talk about the fluoride, but not now. Okay, fluorination. Of course, if you want to introduce fluoride ion to the starting material, we cannot use the same reaction because in the normal condition, fluorine gas is not reactive. Okay? So of course, when fluorine gas is not reactive, these two reactions are not possible in the case of fluoride. Okay? So we will discuss later about the fluorination. So how to introduce fluoride ion to the product. Okay, so I continue. Just remember this one. Okay, how to coordinate the starting material. So you have addition or radical substitution. That's all. Okay, so we finished VCM, I think. So this is the end product of VCM. You can change or convert VCM by the reaction which is called polymerization to the corresponding polymer of VCM. And this one is polyvinyl chloride. Okay. So everybody knows vinyl chloride. This vinyl chloride polymer. So PVC could be used for the fabrication of the plastic tube. This polymer is very chemical resistant, okay, so it can resist a lot of chemical solvent and very stable, and also it could be used outside the house. And PVC has a very high mechanical property, so it could be also used for the production of plastic film. Okay. The second one are very similar. The structure is very similar to VCM. This one is VDC, just a little bit different. So the name vinylidene chloride means you have two chloride atoms, two chloride atoms on the vinyl molecules. This one is the chloride. Okay, VCM only one. Okay, VDC two chloride, VDC or VDM whatever, VDC. Okay. Two chloride atoms. Okay, VDC could be used as starting material for polyvinylidene chloride polymers. So this is the structure of these polymers. So if you can remember something interesting, for the structure of polymer, we use a bracket and small n, which represent the repeating unit of the polymers. Okay. It means, what does it mean? It means that we repeat this unit more and more and more. So in reality, the polymer structure is very long hydrocarbon chain with the same repeating unit over and over. Because polymerization reaction means we connect the monomers with another monomers and a lot of. Okay, so that's why you have a really big molecules for the polymers and very good mechanical properties. Okay, so this is the structure of VDC. VDC is here, VDC. So you have two methods for the production of VDC. Okay, it depends what do you want. The intermediate of the reaction must contain how many chloride? For the final product, you want 2 chloride atoms. So you need how many chloride atoms before elimination reaction? 3. So the intermediate of the reaction must contain 3 chloride. This is chloride, but not very nice. Okay, this one, trichloroethane. This step, okay? So you need to introduce 3 chloride to the molecule, to the 2 carbon. Okay. So the last step is elimination of hydrochloric acid from trichloroethane intermediate, right? How to produce the trichloroethane intermediate? You have 2 methods. Of course, you have addition and radical substitution. They are all possible. If you start from VCM, you have double bond. This is VCM. Double bond and already 1 chloride atom. So you can introduce chlorine gas by addition reaction. So the first one is addition reaction. So you just add chlorine to the double bond here and you produce dichloroethane. But the second one, the second possibility, you start from EDC. And this is the structure of EDC. 2 chloride. Okay? And 4 hydrogen. This is the structure of EDC. In this case, chlorination is also possible, but it's not the same chlorination from VCM. Chlorination of VCM is addition, but the chlorination of EDC is radical substitution. So the 2 reactions are different. If you start from EDC, you chlorinate, you substitute hydrogen by chloride radical in this condition, okay? How many products would be produced from this chlorination? How many products possible? คิดว่า from EDC. How many products possible? 4. ใช่ปะ Why? Just count the number of hydrogen, okay? Because this reaction corresponds to the replacement or the substitution of hydrogen atom by chloride atom. So you can substitute as much as you want. It depends on the number of hydrogen atoms. So in this case, EDC contains 4 hydrogen atoms. So you can substitute 4 times chloride. Okay. So I will show you how many product possible, and it gives just different end product. ไม่มีกระดาษ Okay, so we focus on the second chlorination, okay, from EDC. Okay, so you have EDC. And this is the structure of EDC. 2 carbon, okay. and you just chlorinate and heat. So the first product is the substitution of one chloride, one chloride atom. Okay, and the second one could be this one, 2 chloride atom on 2 carbons. So in total you have 4 chloride atoms, and this one is also possible, 4 chloride atom, but 3 on the same carbon. Why not? Okay, and what else? You can also introduce 5 chloride atoms. And the last one, 6 chloride atoms. And that's finished because you have no more hydrogen to be substituted. Okay? So you have 2 chloride, 3 chloride. Okay, so you can produce a lot of products from chlorination. So how to control the radical chlorination? It depends on the ratio of chlorine gas. If you have a lot of excess of chlorine gas, you tend to produce high chlorinate product. But if you control low concentration of chlorine gas, you tend to produce the low chlorinate product. So the first one, or maybe the second one, a little bit now. But if you have high excess or large excess of chlorine, you risk to produce this one. Okay, so it depends on what you want. Anyway, you can separate them by the process of purification by distillation, for example, because they don't have the same boiling point, and you can separate by the different boiling point. Okay, so moreover, this product and this product, okay, 1, 2, this one, 1, 2, 3, not that one. If you eliminate HCl from this intermediate, you can obtain BDC, right? BDC means you just have 2 chloride atoms on the double bond, right? But what is the product from this intermediate? If you eliminate hydrogen chloride, they give the same product. They could give the same product. 1, 2, 3, 4, 1, 2, 3, 4. So this is possible to eliminate 1 chloride and 1 hydrogen. Okay, so the product could be dichloroethylene. For example, if I eliminate 1 chloride here with 1 hydrogen here, 1 chloride here and 1 hydrogen here, you obtain exactly the same product, Cl. Okay, hydrogen. This is TCE, dichloroethylene. And moreover, for the 5 chloride atom on EDC, 1, 2, 3, 4, 5, if you continue elimination on this intermediate, what is the product? You can eliminate 1 chloride here and 1 hydrogen here. What is the product? You can obtain the vinyl, right? From elimination. You convert single bond to double bond. So this is the vinyl. How many chloride atoms on the final vinyl from this intermediate? 4. 1, 2, 3, 4. So this is beta chloroethylene. The name is PERC. PERC. So I show you on the next slide about TCE and PERC. So trichloroethylene and tetrachloroethylene could be also produced from EDC. follow coordination and elimination. How about the last one? When you have 6 chloride atom, this intermediate can furthermore undergo the elimination reactions? No more, because you have no hydrogen atom remaining on these molecules. Okay, so this one no more product. It stop here. So this is the whole process. Okay, in the production of vinyl chloride components. So you have 4 compounds of vinyl chloride. The first one contains 1 chloride, the second one contains 2 chloride, which is BDC. The third one contains 3 chloride. This is dichloroethylene or TCE. And the last one contains 4 chloride on double bond. This is tetrachloroethylene or PERC. Okay, so what is the application of TCE and PERC? You have a lot of application. Okay, so TCE and PERC are not used in the production of plastic or polymer, unlike VCM and VDC. But TCE and PERC have its own application. Like for example, this is the structure of TCE. The trade name of TCE is trimethylamine, okay, and tetrachloroethylene, the name is PRC. This is the structure. They are the good solvent, okay, but TCE was used as a volatile anesthetic. So what does it mean, anesthetic? It was used before during the medical operation, for example. So you can just fall asleep or lost the consciousness. Okay, before or during the medical operation, the patient must be applied the chloroform, for example, or ether. But chloroform is toxic. Okay, and ether is just flammable. So just take a fire very easy. So that's why we use another alternative product, such as the dichloroethylene. So before, dichloroethylene was used as the volatile anesthetic in the medical treatment, but now it is replaced by another product, which is halogen. We call halogen. So, but similar halogen substitution. But the application of TERC is more limited. Okay, this one is very volatile but very stable also, but it does not take a fire. Okay, but this is a very good organic solvent. Actually, we use this kind of product in the dry cleaning. So you know what does it mean, dry cleaning? It's just the liquid, okay, that you apply during the dry cleaning process of the fabric. And also very good solvent for the hydrocarbon wax. So this is why PERC is used as a detergent to eliminate wax from the metal surface. Okay, so they have a lot of application for the vinyl chloride derivatives. So we have 4 products from the chloride, right? VCM, VDC, TCE, and PERC. Okay, and this is the production process. So you can start from coordination and also elimination, and also you can use the alternative method of coordination, which is oxy-coordination. So I want to summarize, okay, before fluoride product. In order to summarize, I will start from ethylene. If you start from ethylene, okay, you can start from ethylene. So all these products derived from ethylene. So ethylene is converted to EDC. Okay, this is EDC. I don't write the hydrogen atom. I'm too lazy. So this is coordination, okay? And EDC is converted to VCM. This is VCM, okay? By elimination. But EDC is also could be converted to another material in two steps, okay? For example, you can produce VDC from EDC. You can produce TCE from EDC. And also you can produce PERC. PERC, TCE. Okay. So for the conversion of EDC to VDC, TCE, and PERC, it requires two steps, right? So the first step is coordination, and the second step is elimination. Coordination, elimination, coordination, elimination. Okay. You can also convert VCM to VDC, also in two steps. The first one is coordination, and the second one is elimination. Okay, that's all. So you can just try to write this flow chart by yourself. So you can see the connection between the different components. For the vinyl chloride product, you have 4: VCM, VDC, TCE, and PERC. But in this part, you have only 3 reactions involved, 3 types of the reaction involved in this process. Addition, radical coordination, and elimination. That's all. Okay. About fluoride. For fluoride, it's just different because fluorine gas is not as reactive as chlorine gas. So the two types of reactions here are not possible. So I mean a radical substitution, but with fluoride ion, this is not possible. And also the addition of fluorine to double bond, also not possible in the normal condition. So if you want to produce the compound which contains fluoride ion, what you have to do? You have a really limited method how to introduce fluoride to the carbon when fluorine gas is not reactive. How to do? So these two reactions is not possible because fluorine gas is not reactive. So how to introduce fluoride ion? I don't know. Okay, and say in the normal condition. So it can work, but very difficult. Okay. You can use another type of fluoride. You can use fluoride anion F negative charge. Okay. So in this case, we use hydrofluoric acid instead. Okay. So you can use HF instead. So HF can produce fluoride anion. So you can just use fluoride anion. So what is the reaction possible with the fluoride anion? Do you know any reaction with the anion? Elimination? But elimination produces double bond, but in this case I want to introduce or put fluoride in the molecule substitution. So in this case, SN is possible. So SN could be applied in this case. What does it mean SN? You can compare between this substitution by radical and SN. So fluorination in this case can occur when you have leaving group on the carbon and you react with hydrogen fluoride and this is the substitution of living group with fluoride ion. What is the living group? In this case, it could be chloride, for example, and you can produce hydrogen chloride as byproduct. I had one question for midterm examination, okay? But HF มีข้อหนึ่ง for the CFC, yes. So I just asked how to produce CFC. But remember, fluorine is not reactive. So you have to use hydrogen fluoride. But when you have hydrogen fluoride, it's not radical substitution anymore. But this is SN reaction. Okay? Because most of you write something like this. CH react with hydrogen fluoride, which give CF. This is correct. But a lot of students write this reaction and it just surprised me because it's not possible. Not possible because HF just give fluoride anion. Okay, fluoride anion cannot substitute hydrogen. Hydrogen is not living group. Hydrogen could be substituted only when this is the radical reaction only. So this is possible because hydrogen is not living group. I repeat again. I think I told you before midterm already, and I just repeat. I don't know how many times. This is possible, but I still see it from the paper, exam paper. Okay. Okay. In theory, it's not possible, I don't know how to do this. Because if you substitute fluoride to this carbon, hydrogen must live with a negative charge. This is very strange. Hydrogen cannot just live with a negative charge. It's not possible. Okay, remember it's not possible. Okay, hope that I will not see this type of the reaction again in final. Remember, when you have hydrogen fluoride, must be a living group. This is called halogen exchange reaction because you switch or you change chloride to fluoride. Or SN. You can call exchange or just SN. Okay. So come back to our class now. How to produce vinyl fluoride. So what is the structure of vinyl fluoride? You have different vinyl fluoride. It's like you have 4 vinyl chloride, right? You have also 4 vinyl fluoride. But I will not talk about all 4 because some vinyl fluoride is not very important in industry because we don't have direct application, for example. There is one vinyl fluoride that everybody use the end product every day. Maybe if you cook in the kitchen, you must know the Teflon pan. Okay, Teflon is the polymer from the tetrafluoroethylene. One vinyl fluoride. Okay, so how about the fluoride? Vinyl fluoride. I can show you for the full structure of vinyl fluoride. Okay, so here we have, for example, we have double bond, right? So the first one must be only one fluoride atoms. This is VFM. VFM or vinyl fluoride monomer. Okay. The second one contains 2 fluoride. This is VDF, vanillidine fluoride. Of course, we have also 3 fluoride, but I will not talk about this one because it's not very important. I will talk about this one, tetrafluoroethylene. TFE. Because the end product is PTFE, polytetrafluoroethylene. This is Teflon. The trade name of PTFE is Teflon. Okay, but the production of tetrafluoroethylene is completely different from another vinyl chloride, vinyl fluoride. Yeah? So this one is very specific because we cannot use elimination reaction. We have to use the condensation. The starting material is not ethylene, only this one. Okay, this one. TFE is produced from chloromethane, from chloroform, to be exact. It could be produced from chloroform, so you have to condense two C1 unit together to form the C2 unit. But the other product could be produced from ethylene, including VFM and VDF also. So just imagine how to produce VFM. In your opinion, you want to introduce fluoride to the two carbon. So you need elimination, right? To double bonds. Okay, we focus on VFM first. Okay, vinyl fluoride monomer is the starting material of PVF. This is polyvinyl fluoride. The plastic polymer that from the vinyl polymers. Okay, and VDF is the starting material of PVDF. This is also a plastic polymer from the vinyl fluoride, vinylidene fluoride. Okay, so how to produce VFM and VDF? Just think, in your opinion, this one. Okay, this is the last step of the process. Always the same. Elimination. Okay, which type of elimination? I'll show you how to retrosynthesis. And this is the retrosynthesis. I add from the final product to the starting material. Okay, to track which material is possible. If you have this product, know how to synthesize this product. Just one step. So the last step must be always to eliminate to bond. Have to start bond here. CC. Okay. Have to start from single bond. But what can it is the to bond? Always the same. To eliminate for this one. Here, hydrogen chloride. So intermediate here, it must contain one chloride, one fluoride. That's all. And another could be hydrogen. This one is possible. This also possible. Not. For me, it's the same. It must give the same product, right? Okay. So, if you want to produce VFM, you need this kind of intermediate. And the last step is the elimination of hydrogen chloride. Hydrogen chloride. So, how to produce this intermediate? In your opinion, you know all the reactions. Reaction. You have to produce this kind of interface. How to integrate atom? You have living group. SN. Okay. So focus on this kind of the intermediate. One chloride, one chloride, one chloride. อ่ะใครรู้บ้างตรงนี้ได้ยังไงตัวนี้ substitution from which starting material คิดดูสิ TCM มีด้วย BDC you mean double bond BDC double bond like EDC ไปนี้ได้ไงเนี่ยโอเคโอเค you have many method ทำได้หลายแบบนะคะอันนี้แบบนะhere are the reactions. Okay, we have also addition reaction. Addition is possible if form double bond. Yes. เอาใหม่อันนี้เอา substitution ก่อนแล้วกัน I just want to show that two types of the chemical reaction are possible if you want to introduce fluoride, but not with F2, only with HF. So the reactant must be HF, and this is the HF also. But the starting material are different in the two cases, right? Okay. For substitution reaction, you need the substitution of atom by fluoride ion. For example, this one. So, atom could be substituted by fluoride ion. This is okay. You could have another product also. You can substitute all chloride. This is also possible. Okay, so you have a mixture of the product from this substitution. If you want to process with the different reaction, what is the starting material? The same reactant could be used F and H, but not substitution. What is the starting? Yes, you have to start from the double bond and one chloride atom. Yes. So one chloride atom is the chloride. Okay. You can add F. Okay. I have a question. Chloride. What is the name? New chloride monomer. This is ชื่อย่อมเยอะนะคะ Okay. The rule that you have to call Macromolecules of product is the major product. ทำไม Why? You think this one? จริงเหรอ Chloride here. In my opinion, if we follow mathematical rule, it must be the second one. Because if you have carbocation here, it's not stable because of chloride atom is next to carbon positive charge. Okay, I can just show you here. For the addition reaction for BCM, it's just my okay. The first step is hydrogen addition and produce two intermediate. This one or this. And this is not stable because the presence of chloride. Chloride is of the point of view, yes. Chloride atom is high electronegative atom, so it just withdraw the electron from carbon positive. This is also possible. It depends on the effect that you consider, okay? If you consider the electronegativity of chloride, if you consider this one, chloride atom can withdraw electron from carbon positive and carbon positive become less stable. So this one can favor, but in some case, halogen is also electron donor because of the lone pair. So I think both are possible. See which one is the major different substitution and right. Nature of the reaction are different. You have the same reactant, which are hydrogen fluoride and hydrogen fluoride here, but the starting material are different. For the addition reaction, you have to start from double bonds, and for the substitution reaction, you have to start from single bond, one more to be substituted by fluoride. Okay, but for substitution reaction, you need to have two products together, one chloride substitute or both chloride are substitute. So maybe the good choice must be addition reaction because you don't risk to have another product. Okay, so this is how to synthesize the vinyl fluoride. So how to synthesize two fluoride atom here to produce PDF. Okay, so just take a look on the slide. มันไปนี้ได้ไงเนี่ยกันนะคะไปใหญ่เลยดิฉันokay so VDF this is VDFM VDFM polymerize to PVF is the plastic polymer which is used in the solar cell fabrication, okay? And PVF is very stable polymer. It has electronic property, so it used in many applications. Okay. VDFM, this one is VDFM. You can produce VDFM by the similar process. So this is the final step, elimination reaction of hydrogen chloride from this intermediate. So of course, you want two fluoride atoms on the VDF, right? This one. So you must have two fluoride here and one chloride to be eliminated. So the intermediate must contain one chloride and two fluoride. So I just give you the homework to think how to synthesize this intermediate. Okay, how to produce this one. You can use all the reaction that you know. Okay, to produce intermediate product. Maybe by hydrogen exchange, this is possible. Okay. You can play between addition reaction, substitution reaction, the reaction that you want. Okay. So the last one of vinyl fluoride is tetrafluoroethylene. Okay. Tetrafluoroethylene is just different from another vinyl chloride and another vinyl fluoride components because this one is not produced from ethylene, unlike another product. Okay. Because the 6 product before could be produced from ethylene or EDC, right? But this one is not produced from ethylene, but this is produced from chloroform. Okay. So you need condensation reactions because to condense 2 carbon, 2 C1 unit together. Okay. So the last one, I will not show you the mechanism. Okay. Because it's quite complex reaction. But for the first reaction, the conversion of chloroform to the intermediate of the reaction, this is chloro-difluorocarbon, right? CFC. This is CFC or not? What is the code name? The CFC code of this one? 22? จำได้ไหมทุกคนดีเลยใช่ I remember this paper C22 is the CFC code, but I think code of the code I the code HFC or CFC22 and I ask you the structure. That's all. It's very easy. Of CFC22. So CFC22 is the starting material of Teflon. Okay. So that's why it's very important in the industry because the product. This is the monomer and the end product. Polytetrafluoroethylene has a lot of application. Of this polymer is Teflon. Okay, Teflon is the trade name of DuPont, which is the very big chemical company, American. The name is French, but this is American company. Teflon is used in a lot of application from the kitchen to the space because this is lightweight polymers, very resistant. Okay, Teflon is resistant to all the solvent. And all the chemical because it's very stable. So that's why it could be applied on the kitchenware. รู้จักกระทะเทฟลอนใช่ไหม So on the surface, it's covered by Teflon polymer. Okay. PTFE could be also used in the fabrication of aerospace. Because it has very lightweight and very resistant and very high mechanical properties. Okay, so how to produce CFC? You can by exchange. The first reaction is SN reaction. Okay, you just substitute 2 chloride by 2 fluoride and on. That's all. That's all. So it was very easy, but only 10% of students can answer the correct. Okay, no problem. You can recover all the score in final. Okay, that's all. CFC 22. ตอบกันไม่ได้เลยข้อนี้แปลกมาก S and the trade name Teflon ส่วนใหญ่จะรู้จักว่าเป็นกระทะเนาะหลายอย่างมากนะโอเค Okay. Just think about vinyl chloride and vinyl fluoride. Do you have any question? Okay. In this, we have no reactions. We only use the reaction that you know before: elimination, substitution by radical, substitution by nucleophile, means anion, and also a radical substitution. And what else? That's all. So addition reaction from double bond. That's all. Okay. So do you have any question? Double bond. ได้เหมือนกันนะได้อันนี้วิธีที่เขาลงใช้กันกับโปรดักต์ถ้าเราจะทำกล่าวแล้วมันก่อนลองดูก็ได้นะได้ถ้าตามตัวไม่ได้ก็คือได้เลยแต่ในวิธีที่ใช้ในอินดัสทรีเราหมายถึงกับก่อนที่มีตัวนะ4 ตัวแล้วก็ใส่เอเข้าไปแล้วก็ลายออกอีกครั้งพอลายออกครั้งหนึ่งจะได้เดี๋ยวก่อนอีกครั้งแล้วก็ใส่เพิ่มอีกใส่อีกครั้งก็คือทำสลับไปใช่ปะแต่ไม่พอ1 ครั้งใส่แค่ครั้งเดียวอ่ะหรือเราจะเริ่มจาก EDC อ่ะมันต้องเผื่อกำจัดด้วยอ่ะไหนเราลองว่าลองดีไซน์ดูสิถ้าไม่ทำแบบนี้ใช่ไหมมันจะยาวนะได้เดี๋ยวลองดูไหมล่ะมีใช่ VFF มันมาจาก VFM ไงใช่ป่ะโอเคwe can use VFM from VC right is it possible to use the similar process for tetrafluoroethylene you can try we can do it together okay so the question was okay okay so it was like VCM addition with hydrogen fluoride to this one right เดี๋ยวก่อนแป๊บหน่อยนะ fluoride กับ chloride อยู่ที่เดียวกันปะเขาให้อยู่เดียวกันโอเคand elimination once to produce double bond. This is VFM, okay? Can we use the similar process for tetrafluoroethylene? The question was something like this, huh? Your friend just asked me like this. Can we start from tetrafluoroethylene, PERC? You can try. To this one, possible? How many steps? In my opinion, why not? How many steps? 8 steps. So you have to alternate between addition, elimination, addition, elimination, addition, elimination. For example, the first one could be addition. So once you add HF, double bond must disappear. And what to do next? Elimination. Yes, just eliminate. Okay, and again and again and again. So, yes, in theory it's possible. Yes, but in industrial maybe it requires more steps, you know. So we always choose the simple way. So that's why you produce PTFE from CFC22 instead of PRC. But it's possible in theory, it's correct. Just alternate between addition, elimination, 8 times, and you can obtain PTFE. มันทำไปเรื่อยๆได้ Questions? Another questions? Of course, we are open to the new method. If you can invent another method that I don't propose also, but it must be correct and based on the correct theory of chemistry. So everything is possible. I just show you the method that we usually use, but of course it's not the only way, only one method. Okay. Do you need a break before I start the element? Okay. Before break, I check today. So who arrived late before I check? Just give me. Okay. Just give me the student number. Okay. So finally we arrived to the final chapter. Okay. So I want to start something very new. In this chapter we focus on the properties, reactivity, and the production of aromatic compounds. Okay. Sometimes in the book you can find some different vocabulary about aromatic compound. For example, arene. Arene means also aromatic rings. So first, I want to introduce about aromatic compound. So what does it mean, aromatic compound, and what is the aromaticity? Okay, aromaticity is the property that what we call aromaticity. So when I finish the introduction about the aromaticity of the compound, we will talk about the reactions. Okay, so the aromaticity, the main pressure, and reactivity. So we focus on the reactions with the aromatic compound and the reaction that can convert aromatic compound to another compounds. Okay, the reaction of aromatic rings is very specific. You never see before. So in this chapter, we have one reaction very specific to aromatic compound, which is called electrophilic substitution. Okay, this electrophilic substitution is the main reaction in this chapter. You have to understand the mechanism of electrophilic substitution also. And you have some reaction that I summarize. We have 5 different electrophilic substitution. The most important, I chose 5 most important electrophilic substitution in this chapter. I put in the summary that you have to memorize. Okay, and you have to understand about these reactions. So when we finish all the theory about aromatic compounds, we will see in the final part how to produce different aromatic compounds in industry. So, can you give me aromatic compounds that you know? The name, just the name. We have a lot of, okay? Benzene rings, okay? So this is the structure. What is the formula of benzene rings? The chemical formula C6H6. So you have 6 carbon, okay? Okay, we have a tradition to do not draw hydrogen, okay, on the benzene rings. Don't know why, because maybe they are also lazy as me. So we don't draw the hydrogen atom if it's not necessary, okay? So on the benzene ring, you have 6 hydrogen atoms if the benzene ring is not substitute. So what does it mean, substitution of benzene ring? It means you can substitute some group on the benzene rings. So if you substitute one substitution group, for example here, this is the structure of E. One group substitute benzene rings. So of course you have 5 hydrogen. Okay. So when you choose one group on the benzene rings, something like this, it means how many hydrogen on the benzene rings in this case? They are not drawn, but you have to know. 2 substitution group on the benzene ring, so 4 hydrogen atom remain connected to the benzene rings. Okay, so you have to know the presence of the hydrogen atom, even I don't put it in the picture. Okay, so the number of hydrogen atom depends on the number of substitution group. So hydrogen atom is here, 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 here. That's all. So come back to the very base aromatic compound. This is aromatic ring, benzene rings. Okay, this is C6 H6. So they form a ring in hexagonal rings. Okay, but before we did not know about the structure of C6 H6 compound. So we have a lot of proportion and also the theory, but only from I don't know how many when was the structure of the ring that we understand a little bit about aromatic. Okay, so study a lot how chemical how he was I'm not German. And he tried to find out the structure. C6 proposed a lot of structure, and finally he proposed a ring structure, and with the alternation of double bond and single bond inside the ring. So, mean alternation when on and single bond have like this, double bond, alternate with single bond, double bond, single bond, double bond, single bond. So with this kind of alternation of double bond and single bond in the rings, you can have C6 H6 structure. Okay. Before you have the knowledge about the aromatic rings, so Kekulet proposed the name of but now we don't use this name anymore because it's not correct. Okay, this one is not cyclohexadiene. Why? Cyclo because it forms a ring, hexa because you have carbon, and triene because you have 3 double bonds in rings. But after Kekulet proposed this structure long times, another scientist just found out that it's not the triene because double bonds are not fixed in the rings. That's amazing. If you have double bond, 3 position here, the length of the 6 bonds must be different because you have single bond and double bond, the fixed single bond. But in reality, we just find out that the length, the 6 carbon-carbon bonds in the rings are equal. So we have exactly the same type of the bond. So how this is possible? We have double bond, 3 double bond in the ring and 3 single bond in the ring. But how it's possible that the strings are the same? So we find about the compound, which is called phenomenon of the resonance. Okay, this one. Okay, so compound have 6. Okay, The first one is you must have a rings. Okay. So when they are not a ring, they could not be aromatic compound, because aromatic compound must be a ring. Do you know what does it mean, ring? Okay. It could be a small rings, something like this, or a triangle, or I don't know, whatever. Pentagonal rings. Now is also a ring. Whatever member. Okay, aromatic compound must be a ring, but it's not finished. If the ring could have aromaticity, ring must have the resonance form. So, resonance. So first we will discuss about what does it mean aromaticity, okay? Okay, aromaticity means the property of aromatic compound. Property of aromatic compound. So the specific compound could be called aromatic if they have this kind of properties. So the first thing, it must be a ring, of course. So it could be this ring, cyclobutane, pentagonal, or this one, etc. Okay, it must be a closed structure. So if you have a linear structure, we don't call them aromatic. Even this linear structure have another property of aromaticity. They are not aromatic because they don't form a ring. Okay, so the first thing, let's see, is a ring or not. If not, it's not aromatic. Second, you must have something like this. This is the very specific property of aromatic ring, which is called resonance. Okay, resonance in chemistry and in physics don't have the same significance. The meaning of resonance in physics, in wave, resonance of wave, for example, but it's not the same here. Resonance in organic chemistry means, so what does it mean, resonance? Okay, take benzene, for example. This is the structure of benzene ring, okay? You have alternation between double bond and single bond. So when you have alternation of double bond and single bond, in the ring, okay? Resonance means double bond can move to the next single bond. So this happens. So we just move two electrons of double bonds. Electron. How is possible? Because a single bond. If you move the bond to single bond, the next one must be 4. Okay, so you have to duplicate all the double bond in the rings. So you have another position of double bond possible. So you move here. Okay. When you have alternation of double bond and single bond in the rings, resonance can occur. Have delocalization of double bond. Delocalization of occur in this case, it means that you have a resonance. One is the resonance form. Okay, so what does it mean, delocalization? Do you know what does it mean? Delocalization from local. Local means position. Delocalization means you just change the position, so just move. Okay, delocate. So delocalization of double bond means you just delocate double bond to the next single bond. and also you move also another double bonds. Delocalization of double bond can occur also in the linear structure, not only in the rings now, but in the linear structure they are not aromatic because even with the delocalization of double bond is not a ring. Okay, I can propose another example of linear structure. The word delocalization is the common word that we use the movement of double bond to the in the structure. Okay, even it's not a ring or it's not aromatic, you can have delocalization of double bond also. For example, in this type of the structure, for example, it's just an example. So you can move this double bond long, for example, and you have another structure. Okay, this is positive, for example. This is also delocalization, but it's not aromatic because it's not a ring. Okay, so delocalization is the common word to describe how one can move when you have the alternation of double bond and single bond. Everybody understand the word alternation? Alternate, สลับ why alternation must you must have alternation, because if you don't have the alternation between double bond and single bond and double bond, double bond cannot move. For example, if you have this possibility CC. Okay. For the last one, you don't have the alternation, okay? Because double bond and single bond are not alternated. Double bond here cannot move here because I don't put hydrogen, okay, but you have hydrogen here, and this is hydrogen also. So you connect something here. You cannot move double bond here. So what happens if you move double bond here? You have something very strange. Triple bond, and you have already hydrogen here. So the second carbon, or the first carbon on your right, is not tetravalent anymore. So this is not possible. Okay, alternation could occur, but not with the breaking of the bond. You just move, don't eliminate anything from the molecules. If you want to move this double bond, you have to eliminate hydrogen, so it's not possible. Okay, so the localization of double bond is only possible when double bond is alternated with single bond in the system. Okay, and alternation of double bond and single bond and delocalization of double bond is favored because delocalization of electron pi, we call pi electron, means stabilization of the structure. So in chemistry, okay, especially in organic chemistry, if you have one structure with delocalization of double bond, this structure is more stable than the structure without delocalization, because one structure have many possibility of the structure, so it means stability. This molecule is more stable than without delocalization. Okay, so delocalization of electron pi is favored in general because you have a lot of possible structure from delocalization. Okay, the same logic for aromatic compound. Okay, but they are not aromatic because this one is linear. Okay, but they have delocalization. That's all. But in the case of benzene, you have delocalization. Okay, and in the rings. So it sounds like the delocalization around inside the ring is you have the localization because it just turned in the rings. It's like infinity in the rings. Okay, so this is called resonance in the case of aromatic rings. You can switch type. In the case of benzene rings or aromatic compound, you can represent the rings by the resonance form. We use this stuff just to indicate that we don't have a fixed double bond here, but the double bond move all around the ring. So if you see something like this, that is with a resonance. Okay. So this is the very important properties of aromatic compounds. So first, it must be a ring, and second, you must have the resonance. So of course, this one, for example, cyclohexene. The localization of double bond in cyclohexene is no. So hexene is okay. Not. This is a ring or not? Cyclohexene. This is a ring, but have the localization of it's not. So it's very easy. In general, the rings mean you must have double bond alternate with single bond in the rings. It could be a big ring or small ring. The next properties, okay, the third one, okay. The scientists found that the structure of aromatic ring is planar. So what does it mean, planar? In 3 dimensions, okay, in the space. You have something very planned. So the 6 carbon of benzene ring are found on the same symmetric plan. Okay, or on the same, for example, on this paper. So this is how it looks like the benzene ring in reality. Okay, so it means that cyclohexane, for example, okay, this one it must have a planar structure. So this is how we represent in the space. So in the same plan of symmetry, the 6 carbon, it's just plan like a paper. Okay. Cyclohexane. Inversely, this is cyclohexane. Everybody knows that cyclohexane is not aromatic. This one is a ring, but we don't have a resonance. You don't have any double bond inside the cyclohexane, right? This one is not aromatic, and this one is not planar structure. Okay, the 2-dimension structure of cyclohexane looks planar, but in reality, the 6 carbon of cyclohexane are not on the same plan. In reality, you have this type of the structure of cyclohexane. It's not planar. But benzene, this is. So that's why on the benzene, electron can delocate around the rings because you have the same planar of orbital. This is the pi orbital of the carbon. Orbital means where the electrons are. This is electron. So electron can just move around the rings because this is planar structure. Okay, but in case of cyclohexane, 6 carbon are not on the same plan, symmetric. So orbital also, they are not, the orbital of the carbon are not on the same symmetric plan also. So that's why electron cannot move anyway. Okay, on the cyclohexane. This one is not aromatic. So you have to check first, it must be a ring and a resonance, and planar structure comes So all aromatic compound must be planar, especially benzene rings. So you have some kind of interaction, okay, between the two aromatic rings because of its structure also. Okay, it can pack something like this for aromatic stacking. Okay, so in the PowerPoint I have a very quite pretty structure of the planar structure. Okay, so plan. The benzene rings are planned, something like that. So the side view, they are the same symmetric plan, and the projection view also. Okay, this is how what does it mean that electron can move around because of the structure. You have this movement, electron around. This limitation so that not is the aromatic compound very much. Aromatic compounds are very stable. The stable, very difficult to find aromatic compound. So of course, when something is very, you have a limitation of the reaction because not all the reactions possible with aromatic. This reaction destroy aromaticity. Okay, so you have some exception of the reaction possible only with aromatic compound. If the chemical reaction this aromaticity not occur because aromaticity means of the compound. Okay, last property of a compound. This now we come to know one. Just of the number of electrons which are the in low rule only. So what does it mean? Rule. Hooker rules mean you can define the structure of aromatic by using these rules. Okay. Compound would be aromatic if the number of electrons which is the number of electrons. Electrons which are delocalized in the ring must be equal to 4n plus 1 number only, and n must be entity. So n could be 0, 1, 2, 3, 4, 5, whatever. 4n plus 1. So what does it mean? So the last one is the Hooker rule. For n plus 1 is equal to number of delocalized electron inside the ring. Okay, so what does it mean? N must be entity 0, 1, 2, 3, whatever. So the number of delocalized electron must be it must be so if n equal 1, so the number of electron must be เท่าไหร่คะบวก2เท่าไหร่คะถ้าเป็น1 6 6 and if n is 2, number of delocalized electron must be เท่าไหร่คะ10, yes. So if you have electron in the system, aromatic or not? No, it's not aromatic. So how? Number 4. If you have 4 electrons delocalized in the system, aromatic or not? 4. มันมีแค่4ตัว No, it's not aromatic. Example. For example, the structure of cyclobutadiene. Okay, if I ask you, this is aromatic or not? Okay, first, this is a ring. This is cyclobutadiene. This is a ring or not? ใช่วงไหมใช่ดิ Second, delocalization possible? Yes. Yes, because you can move to form another structure. So it looks that cyclobutadiene is aromatic. But this is not aromatic because cyclobutadiene does not follow rules. So just count the number of delocalized electrons in this case. How many electrons delocalized? So how to count delocalized? Just count the number of electrons in bond which can move. So how many electrons in this case? Double bond and bond 2 electron pair. Yes. Total then we have electron 4 electrons can delocate. Okay. So you have delocalization of 2 double bonds in the rings. So it looks like perfect aromatic rings, but it's not because the number of electrons delocalized is 4. So it does not follow the Hooker rule. So how about benzene? What is the number of the delocalized electron here? 6. So the number of electron delocalized in this case, you just count the number of the move electron. So 2 electron for 1 force, right? So 3 electron move around. It means electron can locate. So this is 6, and this for the rule. So it's just a rule, not be careful. Hana effect. Okay, not shake. ลองดูอยู่แล้วใช่ปะ means to be flat. So we can see part structure is aromatic. Yes. It's just the property of compound. So for example, counting of the give the answer because sometimes you have another electron encounter in ionization but not double bond. For example, okay, consider cyclopentadiene. Or not. Why? Can I move electron? Delocalized electron is possible or not? Let me see. Over there now. Yes, you can move, but it stop here. Okay, to this carbon. Okay, so 2 carbon here move to this carbon. 2 electrons, okay, just to this carbon. I have to do the one, okay. So this carbon is positive and negative. So this is follow the rule. But the question is, this or not aromatic? My, because why aromatic? Because it's a ring. Classification. Oh yes, you have the definition. Number of water delocalization not follow the Hooker rules. This one, in this case, what is the number of electron encounter? Yes, 4. So it does not follow the Hooker rules. Another case possible, okay? I change cyclopentadiene to furine. Okay, this is heterocycle. So what does it mean, heterocycle? Heterocycle means you have heteroatom in the rings. It could be oxygen, it could be nitrogen, for example. You don't have only carbon in the rings. So this is heterocycle because oxygen is heteroatom. Okay. In the case of furane, you have to consider something different. Oxygen has 2 lone pairs of electrons. Okay. So you can consider furane like cyclopentadiene, which is not aromatic because the number of electrons encountered in delocalization does not follow Hooker rules. You can consider like this, but it's not correct because in this case, 1 lone pair of electron of oxygen participate to the delocalization also. So just be careful. Don't count only the number of double bonds. It must be So what does it mean? You can delocate double bond. Okay, is possible. Okay, you move also this double bond and this. Can you move this to this bonding between carbon and oxygen? Oxygen must follow octet rule. So oxygen cannot have more than 4 arms. So if you move double bond here, imagine oxygen will have 2 double bond and 1 lone pair. So it's not correct. You have to follow octet rule. Okay. Then 1 double lone pair. But this carbon, okay, I have to put hydrogen also to understand. Let's see, localization never atom. Okay, so you don't eliminate from localization. It's not correct. This carbon, the last one, contain 1 lone from the localization of double. This carbon follow octet rule or not? This carbon, the maximum 4 arms, so I don't violate the octet rule. 1, 2, 3, 4. But how about the charge? This becomes negative charge. And how about the charge of oxygen? This is a positive charge. Okay. So in this electron which encounters or participate in the delocalization, the number of this electron is electrons 1, 2, 3, 4, 6. In this case, the number of electrons participate in the delocalization is 6. So this follow the rules. So furane is aromatic. Okay. A multiple system could be also aromatic. What does it mean? A multiple rings. The system which is composed by more than 1 rings. For example, naphthalene. Okay, this is double bond of naphthalene. This is the structure of naphthalene. All the bonds here can move delocalized around the two. So this is aromatic bond. So just first, this is a ring. Yes. Second, localization possible. This is possible for the delocalization of electrons. You can try to move by your just move. Okay. So you have two rings in resonance, and how many electrons? Yes, how many electrons delocalized? เท่าไหร่คะ 1 2 3 4 5 6 7 8 9 10 so 10. This is 10. So number 10 follow Hooker rules on ตามกฎไหม Yes. Naphthalene is aromatic. You have also tricycle like the structure is quite difficult. Something like this. Anthracene is also aromatic. You can try to delocalize it from here. Okay. So I show you about what does it mean aromaticity. Okay. So first, if it's not arranged, it cannot be aromatic. And you have to see some alternation of double bond and single bond in this system inside the rings. And if you have delocalization, you have to count number of electrons which can move. And you have to follow the octet rule. When you move electron, you cannot break the bond, and carbon cannot have more than 4 arms. Oxygen neither. Okay? And you cannot eliminate hydrogen from delocalization. This is the basic rule for delocalization. Okay? Just move and don't break the bond between carbon or carbon hydrogen. So now you are able to distinguish between aromatic compound and non-aromatic compound. Okay. So what I focus in this chapter, I focus on the benzene rings only. Okay. What is the reactivity and chemistry of the benzene rings? And this could be applied to another aromatic rings also. We have the same theory. Okay, but I take only benzene for the model, for the role model, not another type of the rings. Okay. So the most important in industry, you have 3 aromatic compounds, very important in industry, which is called BTX chain. Okay, so you have see the structure there, the benzene. Toluene, ET, okay, X form xylene. So in industry, we focus on what we call a BTX chain. Okay, in aromatic industry, BTX chain means the product, aromatic product, which derive or convert from the 3 aromatic compound here. B means benzene. Okay, T means toluene. Toluene. X is xylene. Okay, and so in the production, you can produce benzene, toluene, and xylene. and you can convert benzene, toluene, and xylene to another product. You have a long list of the secondary product from BTX chain. So this is the structure of benzene. Okay, toluene is the methyl benzene. So you have one methyl group substitute to the benzene rings. How about xylene? Xylene is dimethylbenzene. Dimethylbenzene. So what does it mean? You must have two methyl group substitute on the benzene rings. How many isomers of xylene possible? How many? Just look at the position of the two methyl group, okay? In the case of xylene, you have 3 isomers. When you have 1, 2, 1, 3, and 1, 4. On aromatic compounds, the position of the substitution group is very important. They don't have the same when you don't have the substitution. Okay, 3 are benzene. The position of the 2 methyl on the benzene ring is very important. You don't have the same property for the 3 compounds. 1, 3, 4. In order to identify, we have the specific system, specific nomenclature system for especially for aromatic compound. Okay, when you have 1, 2, this isomer is called auto isomer. Okay, this is auto position. 1, 3 is meta position. ME, meta position, and 1, 4 is para position. Okay. Everybody know the word para because of paracetamol, right? Paracetamol is also aromatic rings with two substitution group on the para position. I think I have some example about paracetamol, but paracetamol is a common name, not systematic name. This is para, I don't remember, carboxylic something. Okay. So this chapter I focus on the BTX chain. Okay. So first I want to focus on the reactivity of the benzene ring first. Okay. And you will see how to convert BTX to another by the chemical reaction possible with benzene rings. Okay. So in the benzene rings you have a resonance. This part is aromatic, right? So it means stability. They are very stable. Very, very stable. So the reaction, is destroy the aromaticity of the ring is not possible. You have only some exception that you have to memorize. Okay. For example, this is stable. Okay. The first one, the double bond in the ring of cyclohexene. Okay. The reactivity of this double bond and the reactivity of the double bond. Okay. Focus on this double bond. Focus on the bond. They have the same reactivity. Okay. Hexene is not a aromatic. But benzene is aromatic. Okay. This is the difference between two compounds. Okay. We can try some reaction on the double bond. For example, addition reactions. In the addition reactions, for example, bromination, the first one. you react one bromide to double bond in order to convert double bond to single bond with two atoms of bromine. This is addition reaction. We call bromination. Okay. Double bond is this and convert to single. Okay. This is possible, and this addition is also possible. Addition of sulfuric acid. And remember, I talked about this addition in the synthesis of alcohol. Okay. So you can obtain the product of addition with the loss of double bonds. This is anti. Okay. Since double bond in the just friendly with the same condition, okay, we sulfuric to get addition. So expect kind of this one. ไม่ค่อยสวยเลยนะชื่อ this one. But we don't get this product. Why? It doesn't work on the why? Because benzene means stability, right? Aromaticity means stability. So if you lost aromaticity, it means that you lost also stability of the compound. The product from the addition reaction, the red one, this is aromatic or not? That one. อันนี้ยัง aromatic ไหม? Why? The product is no more aromatic because you lost one double bond and you also lost aromaticity of the rings. Okay? So the dibromocyclohexadiene, okay, it could be the name. This one is not aromatic. So you lost aromaticity of the compound, so it does not occur. Same condition will happen, okay? So that's why benzene ring is very stable one. So double bond of benzene in the double bond rings does not have the same reactivity as the double bond in the alkene product. Because if it reacts and you lost aromaticity, it's not good for the product. In terms of thermodynamic, right? You always produce something stable, more stable than the starting material. If you produce something less stable, it's against thermodynamic rule. Okay, it's always like this in chemistry. We talk about stability of the product because we tend to produce something stable, or we tend to stabilize the system in general for the chemical reaction. So, for you some exception. I said it's not possible, but there are one or two reactions that destroy the aromaticity of the compound. That rise now, but they are just an exception. Okay. Okay. So before I start the reaction or reactivity of the aromatic rings, I want to talk about the nature of the aromatic ring first. So move to this table for the common name. Then you have to memorize. I asked you, and I you to memorize the name. So for the benzene rings, we usually use the common name, not the synthetic name. So what does it mean, the common name? Common name means this name does not follow the system, okay? The name that we commonly use. For example, we know that in a phenol, for example, phenol is the common name of benzene substituted by OH group, benzenol. But we never call this one benzenol. We call phenol. Okay, you have to know this one is phenol. Okay, so how about the aldehyde? The aldehyde of the benzene is benzene carbonyl, right? But the common name is benzaldehyde. And benzoic acid, the carboxylic acid. connect to the benzene rings. And when you have the vinyl group, this is vinyl benzene, right? Okay. The systematic name is very normal, but we use the word styrene. I don't know. Everybody knows styrene because the end product of styrene is polystyrene. Polystyrene in plastic. This is the white foam that we use in the insulator, for example. Okay, vinyl benzene styrene. Acetophenone is the ketone. Methylphenyl ketone. Acetophenone, anisole for the ether, and aniline for the amine. Okay, you can use this common name for the nomenclature also. So how about the nomenclature? First, if you have only mono substitution, there is no problem about the position because you have only one substitute. So you just use the name of the substitution group in front of the benzene word. Okay, bromobenzene, butylbenzene, nitrobenzene, for example. It's very simple. But it's a problem when you have more than one substitution group. In this case, you have to identify the position. Because when you don't have the same position, they are not the same compound. Okay, they are isomer with different property. Ortho, meta, for the 1, 1, 1, 2, 1, 2, 1, 3, 1, 4. Okay, so if you have more than 2 substitution group, you always use the word ortho, meta, para. Just identify the main substitution group and put number 1 on this main substitution group. Okay. Okay. We can try to name these aromatic compounds. Start from this one. This is very easy. 2 chloride atom on the benzene rings. What is the position? 1, 2. So what is the name of this isomer? Ortho. Yes. This is ortho dichlorobenzene. We use O for ortho. Okay. O, M, and P. O in italic, and M also in italic and italic. Okay, ortho dichlorobenzene. And how about this one? You have different method. Okay, it depends. Which is the main substitution group in your opinion, nitro or methyl? What is the methyl benzene? Toluene, yes. So you can use toluene. Because this is toluene, right? Methyl benzene is toluene. So methyl benzene is not common name. The common name of methyl benzene is very well known. This is toluene. Okay? So this is, what is the name? This group is nitro. Nitrotoluene. What is the position? Ortho meta para. This one is meta nitrotoluene. Toluene คือตัวไหนtoluene คืออันนี้คือtoluene. If you don't like toluene, you can use methyl benzene, nitromethylbenzene. แต่ส่วนใหญ่ก็จะพูดtoluene. So methyl common name. This is the common acetophenone. If you have a common name, use a common name. If you don't have a common name, use a unique name. So this one is fluoroacetophenone. Okay. What is the position? Para fluoroacetophenone. Okay. Phenol. And some additional information. This is phenyl. When benzene ring, when the benzene ring is substitution group, I mean when the benzene ring is connected to something, this one is phenyl. We call this one phenyl. when the rings is substitution group to another compound. This is phenyl. Okay. And this one is why benzyl. When you have benzene and C, one carbon, this one is benzyl. It could be useful for the nomenclature. Phenyl group, benzyl group. Question? So if you agree, want to move to the reactivity, it's very big part and it needs a concentration. So first I want to start the reactivity of the benzene rings. Okay, so when you have aromatic compound, you have to consider two part difference. Okay, what does it mean? You have aromatic rings. And you have also a substitution group. Substitution group means the group which is connect to benzene, which substitute hydrogen on the benzene. This one. This is substitution group. We use the word substitution group, okay, just to represent the group which are connect to the benzene rings, which is not hydrogen. Okay, so all the group which are not hydrogen is considered to be substitution group on the benzene rings. Okay, it could be any group but not hydrogen. So this is substitution group. And this is the rings, okay, the aromatic rings. An aromatic ring and substitution group don't have the same reactivity. It depends. Sometimes when you have the reaction, you have to think about which part react in this case. Sometimes substitution group react, but sometimes aromatic ring can react. But they don't have the same reactivity. Okay? So for the substitution group, I consider separately because they don't have the same reactivity. For the substitution group, you can all the reaction is possible. So all the reaction is possible. The reaction that you know before, they are all possible with the substitution group. For example, SN is possible, addition is possible, substitution, radical substitution is also possible. Okay, and what else? All the reaction, oxidation, reduction, etc. Okay, so all the reaction can occur on the substitution group. Sometimes we call a side chain when you have a chain. Side chain means hydrocarbon chain substitute on the benzene ring. So all the reaction can occur on the side chain on the substitution group without touching the aromatic rings. Okay, so we don't touch aromatic ring. You just react. Substitution on everything on the substitution group. So you can use all the reaction that you know. No exception. Okay? But how about aromatic rings? Aromatic rings can undergo only a very limited reaction because of stability. Okay? You have one rule. If you destroy aromaticity, product become less stable, so it's not good. But we have some reaction. Some exception, okay? So we have a really limited reaction which happen with the aromatic ring, not the substitution group. So for example, this is very important, the reduction. This is an exception, okay? reduction is possible in the benzene rings, but is an exception. It's not a normal condition. You have reduction. The first reduction is hydrogenation. This is what you have to remember, okay? And the second one is called Birch reduction. I will explain later what does it mean, Birch reduction. And I put two stars here. The most important reaction which occur directly on the aromatic rings. The most important is electrophilic substitution. This is the main reaction in this chapter. You have to understand this one. I beg you to understand this one, okay? I put 3 stars. Just to say that this is very important. Okay, give you some example about substitution group and the ring. For example, you have double bond here, okay? No, the aromatic ring here with, for example, CH2, CH3. What is the name of these benzene rings? ชื่ออะไรคะ ethyl benzene ใช่ปะ ethyl benzene. Okay, so I put one reactant and heat. Can you give me the product? Okay, and I have another question. The same. No heat. You know all the reaction here because I talk about this, I don't know, 100 times. So what is the first reaction? Radical heating. Radical substitution. But what is the product? Can you substitute chloride? Okay, how many hydrogen here? You have hydrogen here. How many hydrogen on the benzene rings? 5. You have 5 hydrogen of the benzene ring and 5 hydrogen of ethyl group. So I said, I told you that radical substitution means the chloride radical can substitute hydrogen, right? But which hydrogen? This is possible to produce chloride here. Okay. Can you substitute chloride on ethyl group? Yes, because I say all the reaction which occur on the substitution group can occur, no exception. It just occur like it's not aromatic. Okay, so it's possible that you substitute chloride to ethyl group here and you can produce this product. But you can expect this one too. Maybe this one. By radical substitution. Because I say, okay, you can substitute hydrogen by chloride, so why not this one? You want to substitute this hydrogen by chloride. No, this one is not possible. Because radical coordination, okay, cannot occur with aromatic rings. It's not that easy. If you want to put chloride to aromatic rings, you cannot use radical coordination. This one is not possible. You have to use electrophilic substitution, not reaction. Electrophilic substitution. That I will show you. Okay. I move to the second reaction. So you obtain this one, and you see you don't touch the benzene rings. So the benzene ring just stay intact. Okay. So it's the same here, but you can react only the side chain. So how about the second one? This is no heating, so you can think about addition reaction, right? This is possible here? No. Because you cannot add chloride to double bond of aromatic rings. Because aromatic ring will lose aromaticity. But this is possible, this product. This aromatic compound can undergo addition? Yes, but double bond on the side chain only undergo addition, but not double bond in aromatic rings. For example, okay? So this is what I want to make you understand. You have to separate the reaction which occur with the substitution group and the reaction which occur with the aromatic ring. You have to separate them, okay? So for the reaction which occur with aromatic rings, you have only limit, but for the substitution group, all is possible. For example, another one. Do you know substitution? Sn, right? Everybody know Sn now. CH, Cl, with what idea? HF, สมมตินะคะ HF. Okay, Sn reaction can occur. If you have chloride here also, can you substitute chloride on benzene rings? Of course not. Yes, but you can substitute this chloride because this chloride is on the substitution group. So you can just consider like no aromatic here, just the normal chemical, normal carbon. Okay, so this one, for example. Okay, so first I want to show you the reduction, which is an exception of aromatic compound, because this reaction destroy aromatic rings. Okay, destroy aromaticity, but it can occur in very strong condition. Okay, so now we focus on reduction. You have two types of reduction possible of benzene rings. The first one is hydrogenation, and the second one is Birch reduction. So the difference between these two reductions is just the number of double bond which is reduced. Okay. So when I say reduction in the case of double bond, I mean double bond is hydrogenate. So double bond must be converted to single bond in reduction process. Okay. So first, hydrogenation. We have two types of reduction. Okay. So the first one, hydrogenation. Hydrogenate means you add hydrogen to double bonds. Okay, this is the addition reaction, but in very strong condition. You need a specific catalyst. You need acid. Okay, so three moles of hydrogen gas are required. You hydrogenate all double bond here. You convert benzene to cyclohexane. This is possible. Okay, 100%. But this product is not aromatic anymore. So it means that this reaction destroys aromaticity of the compound. Okay? So it's not a common reaction. And the first reduction, this is called Birch reduction. It can occur with aromatic rings also, but very specific reaction. You reduce only one double bond, not three double bonds. It's unlike hydrogenation. Because in hydrogenation, you reduce all the double bond here, and no double bond remains in the ring. Okay? For Birch reduction, you still have two double bonds in the product, but the double bond change the position. Okay? So this is very specific. This one is aromatic or not? not only the number of electrons but also the position, because double bond here are far, so you don't have the information. You have single bond and single bond here, so it's not information between double bond and single bond. So 1,4-cyclohexadiene and cyclohexane are not aromatic. Okay, so in this case you just lost aromaticity. So it's only an exception. Okay. So I can show you another reaction which occur with the substitution group, not the aromatic ring. For example, the free radical halogenation, I show you in the paper here. So the free radical halogenation can occur with the substitution group, but never on the benzene rings. Okay, so you just touch the benzene group here. So you transform to the benzyl radical, which is quite stable. Okay, this radical is quite stable because you have the electron. Okay, this electron is more stable when you have aromatic rings. Okay, I will explain about stability later. Okay, and you coronate. Okay, you have benzyl chloride. Why benzyl? Because you have CH2 here. CH2 benzene. This is benzyl group. Okay, benzyl chloride. So it just occurs like another product, the free radical halogenation, but not on the aromatic rings. Oxidation is also possible, but not inside the ring. You have also oxidation of aromatic rings, but I will show you later. I think in the last part when we produce oxidation product of benzene. I will show you how to oxidize benzene rings, okay? But in the normal condition of oxidation, you can oxidize until group. Okay, this is the until benzene. You can oxidize until group to benzoic acid. The specificity of this oxidation of until benzene is that whatever the number of the carbon, okay, you oxidize all. I mean, you just cut all everything and you get benzoic acid. For example, you can start from methyl here. You oxidize this carbon to carboxylic acid. But if you start from isopropyl, this is secondary carbon, okay? You also oxidize to carboxylic acid. So you see methyl or isopropyl, all the until group are oxidized to the same group. So it does not depend on the number of the carbon here. You oxidize all. Okay. But be careful about oxidation when you have another group on the benzene. Another group could be also oxidized. For example, amine group, NH2. Amine could be oxidized to nitro group. So finally you have nitrobenzoic acid. So the oxidation must have the oxidizing agent here. So oxidizing agent could be chromic acid. This is the common oxidizing agent. I think I explained it, last week about oxidation, right? Chromic acid, something. So it's not the first time that I talk about oxidation and chromic acid. Okay, another reaction, SN reaction, can occur on the substitution group also. This is the living group, okay? So you can substitute chloride by or the nucleophile particle and you get the product, but not directly on the benzene rings for the SN reaction. Another type of the reaction, last one is, for example, polymerization. It also can occur on the double bond of the substitution group. For example, styrene. What is the structure of styrene? Okay, this is the structure of styrene. We have double bond here. You can react double bond of styrene, but not double bond of aromatic rings. And you can connect styrene together, okay, to form this polymer. This is the structure of polystyrene. by polymerization. Polymerization is also the reaction which occurs on the substitution group, not on the aromatic group. Okay, so, but okay, it's better to stop here because the next step will be electrophilic substitution. And this is very something new, okay, something very new, and it requires very high concentration, okay, from you. So next week I want to focus on electrophilic substitution. Okay, this is very important reaction, and I hope to finish next Monday. So next Monday afternoon, I start at 1:30, okay? You have to confirm about the room. It must be on the second floor. But if no room available here, we can go back to CHE building, okay? Maybe room number 226, huh? Okay, so you have to inform me about the room, okay? You have my number. Okay, thank you very much.